All right, everybody. So let's take our ideas of the hybridization and expanding this octet rule. Let's just talk about, let's look at actually some structures and draw some structures this way. But as you've probably figured, there's going to be a little issue with drawing these electron dot structures the old way, okay, because the old way follows the octet rule. So what happens when you have exceptions to the octet rule and you have to draw your Lewis structure? So there's a slight different variation to this. This way works with your advanced ones. It also works with the easy ones. All right, so I'm going to show you a technique on how to do this really quickly, and then we'll do some structures and see how this works. So again, we're accommodating all molecules here, 2, 4, 6, 8, 10, and 12, not just the octet rule. So it warrants something a little different, okay? So here's an alternate method to do this. So what are you going to do first? Number one, first things first, is to add up the total amount of valence electrons that you have in the molecule, a total number, okay? So that's taking all the elements and adding them all up, okay? Next, that's going to be the amount that you need to draw, okay? Then we're going to take the outside elements, attach them to the central atom, okay, with single bonds, okay? So you have to determine what the central atom is. Again, the central atom is one that forms the most bonds. I think we're getting used to that, right? Group 14, 15, 16 typically is the central atoms, okay? You're going to bond everything else to that central atom with a single bond. Okay, we're going to complete the octet of atoms attached to the central atom. So all the outside elements complete their octets, which means they get 8 valence electrons. Okay, not hydrogen. Okay, remember that hydrogen does not get an octet. Everybody else does. Okay, please make sure once step 3 is done that you check the electrons that you need, okay, are equal to the electrons that you have drawn when you finish step 3. Okay, you're going to check it off. Make sure the need checks off what you have drawn. If they do check off, then you've drawn enough electrons. Then you don't have to add any more electrons to the structure. Now, 5 is important. 5 and 6 are if. If you need more electrons and you haven't drawn enough, then you're going to add lone pairs to increase your total. All right, that's important to know. Okay, so again, I know it's crazy looking at all these rules, but once it starts to flow quickly, you'll see it's easy. Okay, and number 6, if the central atom needs an octet and you've drawn enough, you can't add more, right? You can't have more than what you need. Okay, you can create double bonds and triple bonds. So step 5 and 6 are going to adjust your structure just in case that this step doesn't work. Okay, and we're going to get to that a little bit. So based on this, you can do that, or both, okay, if you need to. All right, again, that's going to be your judgment call. All right, so let's do a quick structure. Let's just say I have SF6. All right, so let's do number 1. So add up the total. So sulfur, if I look at the periodic table, has 6 valence electrons. Fluorine, if I look at if the periodic table, has 7 electrons, but there are 6 fluorines. So it's 7 times 6 of them is 42, okay? And if I add them all together, I get 48 electrons. That's what I need to draw. Okay, so let's do that again. Sulfur has 6 valence electrons, is 1 sulfur. There is 6 fluorines. Each fluorine has 7 valence electrons in the periodic table. 7 times the 6 of them is 42. Okay, so basically I need to show 48 electrons in my structure. All right, so that's step 1. Step 2, outside elements attached to the central. So since sulfur forms the most bond, I'm going to put sulfur in the middle, and I'm going to attach my single bonds. And like we know, to spread out things evenly. So basically, you're going to even things out the best you can. Again, you don't have. I'm not going to get out a protractor and check you, but even things out evenly. Okay, and then these would be Fs that will attach. There's 6 of them. We're going to put them around the molecule. F, 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 F. Okay, be careful how you say that. All right, and then we're going to go down and we're going to, let's see. So we attach them with single bonds. Now I'm going to complete the octets attached to central atom. So let's complete my octet. 1, 2, 3, 4, 5, 6. The bond is 7 and 8. 1, 2, 3, 4, 5, 6. The bond is 7 and 8. 1, 2, 3, 4. The bond makes 8. Again, we're going to go all the way around the molecule. And I'm sure you're having so much fun doing this. I happen to like this. Okay, so I go 1, 2, 3, 4, 5, 6, and that. Okay, so that completes the octets of everybody. So everybody around the central atom has an octet. So that takes care of lesson not lesson, but step 3. Okay, now it's 4. Check the number that you need with the electrons you have drawn. So let's look around and count them all. Well, this has 8 here, right? There's 8 here, and this happens 6 times, right? So the 8 valence electrons times 6 bonds, 6 elements, is 48. So wait a second. The 48 that I drew matches the 48 that I need. So I'm okay with step 4. All right. So I don't need to do step 5 or step 6 because I'm satisfied, right? Sulfur has what it needs, right? It needs an octet. It does. It's sulfur. Sulfur it needs an octet or more, okay? Because it's in period 3. All right. And I have enough electrons. So this becomes the structure. Now, what I want to do is talk about my hybridization. Check the total pairs around the central atom. The total pairs around the central atom is 6 bonding pairs, no lone pairs. Okay? So what I can do is I can look on my chart on page 24, okay, and look up 60 and find out that 60 happens to be octahedral. Octahedral. Okay? Or octahedral. Octahedral is my shape. My hybridization is what makes 6 total pairs. 6 total pairs would be sp3. That makes 4, right? 1 plus 3 is 4. D2. Okay, so that's my hybridization. That's my shape. That's my bonding pair, lone pairs. That's my dot structure. Okay, and since it's symmetrical, I'm going to call it nonpolar. All right, so these are all the things that you could say about this molecule. All right, so that's a good way to practice things. All right, and if I need to help you, you're going crazy. Look at this cat. All right, so a couple things we're moving forward. All right, and then sometimes this can happen. Sometimes it's impossible to draw a single Lewis structure for a molecule due to the number of electrons and choice of bond placement. This is called resonance. So we're going to see what has resonance. The real molecule would be an average of these possible structures. So sometimes this happens. So let's do a couple. All right, so we did SF6 already. Okay, let's do that. Let's take a look at SF6. We've done that already. So we have S is going to be the F6. So I'm going to say we've done that already. That's okay. All right, SF4. Let's take a look at this one. This is interesting. If I take S is going to have 6, correct? F is going to have 7 times 4 this time is 28. All right, and I'm going to go 34 total valence electrons. This is what I need. All right, I'll put my S in the middle, put my bonds around it, okay? However, okay, and then I'll put my F's where I need to be, put my F's and single bonds around it, just like we did before, very similar to what we did up there, okay? We're going to go, we'll put our dots around here, my octets around where I need to. Okay, which is fine, okay? And then what I'm going to do is I'm going to go and say, okay, let me see what I got here. So I have 8, 16, 24, 32. So I drew 32. But wait a second. I drew 32. I need 34. Okay, so what am I going to really do here? So my answer to that is step 5, right? In step 5, if I don't draw enough, then I'm going to have to add a lone pair to the central atom. Okay? And now I add a lone pair to make 34. Now I'm good. Okay? So my total pairs is 4, 1. Okay? Which if I look at page 24 on my chart, that's going to make me seesaw. Is my molecule. Isn't that cute? Seesaw. Okay? And that's going to be an sp3, which is 4. I need a total of 5, so I'm going to have to put a D there. So I'll make it sp3d1. Okay? And that becomes my hybridization. So my hybridization is sp3d1. My shape is seesaw. Okay? And my structure is as follows. And of course, this is definitely asymmetrical. So this would be a polar molecule or a dipole. All right, let's take a look at ozone. Okay, ozone has oxygen is 6 valence electrons times 3, which is 18 valence electrons. So we're going to go oxygen, bonded to oxygen, bonded to oxygen on both sides. Okay, so I need to draw 18. I'm going to give everybody bonded to the central atom an octet. Okay, looks pretty good. All right, now I'm going to count up my valence electrons. I'm going to have 8 here and 16. So I drew 16, and I got a problem again, don't I? Okay, I don't have enough electrons. So I'm going to put a lone pair on the central atom. So now I'm going to make that 18, which checks out. We're good now. But there's a problem still. And the problem is if you look at oxygen in the middle, oxygen in the middle only has 6 valence electrons attached to it. 1, 2, 3, 4, 5. Well, 2, 4, and 6. So 1, 2, 3, 4, 5, 6. Okay, and oxygen is an element that needs 8. Okay, it's got to have 8. Okay, so if I add another lone pair, I'm going to go over my amount. Okay, and that's a problem. So what I'm simply going to do is I'm going to take, this is where things get interesting. I'm going to remove this lone pair. I'm going to scratch it out. Okay, and I'm going to share them. I'm going to share an extra pair with the central atom and create a double bond. Okay. Now, in order to make a double bond, you have to get rid of another pair from an atom. Okay, and we're going to have that set up. So that solves the problem, doesn't it? Because now we still have 18 electrons, but we've shared another pair with the central atom so that the central atom now can have enough. So it's 2, 4, 6, 8 around this central atom. This atom still has 8, and this atom has 8. But there's another problem. The problem is I used this oxygen when I also could have used that oxygen. So what we're going to have to do is draw another structure that shows that I could have used that oxygen also. So I'm going to draw another version of this, and that's called resonance. When an element has resonance, you can draw it in multiple ways like that. Okay? And that simply means that ozone is actually both of these structures together at the same time, which means this double bond is spread out over the whole molecule. Okay, so this double bond is actually in both places at the same time. All right, and that's important to know. So this is called resonance. That's a resonance molecule. Okay? Now, total pairs around the central atom, not counting double bonds, right, is going to be 2, 1, which is bent. Hybridization, only single bonds. Only single bonds, right? So this is going to be sp2 because it matches the total pairs around the central atom, right? Okay, and we're going to call this resonance, all right? And last but not least, this is we'll do more practice with this, okay? Last but not least is boron. Okay, boron has 3 valence electrons. Chlorine is going to have 7 times 3, which is 21, for a total of 24. We're going to put boron in the middle. 1, 2, 3 bonds to chlorine, chlorine, and chlorine. 2 dots, 2 dots, 2 dots. Again, we'll go quick here. Again, chlorine's going to have 8 dots around it, 8 dots around it, 8 dots around, 8 dots around it. Okay, and that looks pretty good. So I need 24. I drew 24. Okay. However, boron does not have an octet, but remember, boron is an exception. It's okay this way. So we are good, and we are good. Boron can have 3 bonds and be okay with it. This is going to be sp2, which is a 3, 0. Our shape, trig, planar. All right. And probably non-polar because it's symmetrical. All right. So again, a lot of stuff to do here, guys. A lot going on. We're going to definitely practice a lot of this, but this is a good way to do it. Again, you may want to rewind and go through ozone. That has interesting problems to it. All right. All right. We'll talk to you soon.